Okay, we're going to talk now about premises that make a general claim of some kind and how to evaluate them. So we'll start by talking about universal generalizations or universal claims or statements. Those are claims about what is true of all things of a certain kind or in all of a number of different situations. So here are some examples. All leopards are carnivores, makes a claim about all leopards. The government should ban advertising of all products that are a health hazard. Whenever it rains, the cricket match is cancelled. All trees and shrubs that bear edible fruit have five-sided flowers. Killing a human being is never justified. That's making a claim about all killings of human beings, and it's saying that none of them are justified. Anyone entering the country must have an appropriate visa. All the cards on the table are aces or fives. The only flightless birds are penguins. In other words, all birds that are flightless are penguins. That happens to be a false generalisation, but never mind. And finally, look at this one. If a person is under 18, then they're not eligible to vote. That's a general claim because it's not talking about any particular person, it's talking about all people under 18 and saying none of them are eligible to vote. Now, sometimes the term generalisation is used as a term of criticism. It implies that the claim being made is false. We are not using the term in that way. Some generalisations, universal generalisations, as we're using that term, are uncontroversially true. For example, all leopards are carnivores, or it might be true of a particular set of cards on the table that they are all aces or fives. Some are false. The only flightless birds are penguins. I already mentioned that one's false. All Australians live in cities. Some are controversial. This one, all trees and shrubs that bear edible fruit have five-sided flowers. I read in a book recently. No idea whether that's true or false. I'd have to do more research to find out. Killing a human being is never justified. Well, you will find ethicists and philosophers and ordinary people who dispute that claim that killing a human being is never justified. Never justified under any circumstances. Some people think, well, there are situations where killing is justified. So the point I'm trying to make is that some generalisations are perfectly true, and so you cannot criticise a claim or a premise just by referring to it as a generalisation. You can't say, well, that's a generalisation. Yeah, so what? That doesn't necessarily mean it's false. If you've got a criticism of the generalisation, make it. As we'll see in a moment, the right way to critique a generalisation is to provide a counter-example. So that's what you need to do in order to evaluate or critique a universal generalisation. Provide a counter-example. You can't just say, it's a generalisation. A useful tool for thinking about universal generalisations are these circle diagrams, which we introduced in the topic on deductive validity. So here's a diagram representing the generalisation that all leopards are carnivores. So we have a small circle representing the leopards and a larger circle representing the carnivores. And as you can see from the diagram, any leopard, anything inside the small circle, is automatically inside the big circle. So every leopard is also a carnivore. The converse isn't necessarily true. There could be a carnivore that wasn't a leopard, tigers, lions, and so on. When people make a generalisation like this, all leopards are carnivores, they usually have in mind what you might call the domain of the generalisation, which is the wider category that both leopards and carnivores fit into. In this case, it would probably be animals. So you can read this claim as saying, amongst the animals, all the leopards are carnivores. So we can represent that on these diagrams by surrounding our two circles with a big box and labelling that animals, or whatever the relevant domain happens to be. Here's some more examples. So for this generalisation, written in conditional form, if a person is under 18, then they're not eligible to vote. Everyone who's under 18 is a person who's not eligible to vote. The domain here depends on the context, but they might just be talking about the people in a particular nation, Australians, for example. So generally, the general pattern is this: if you have a generalisation of this form, all A are B, or if something's A, then it's B, then you represent it on a diagram with a small circle representing the A's, which is completely enclosed inside a bigger circle, the B's, because we don't want this to imply that all B's are also A's, so we want to leave open the possibility that there are B's which are not A. Here's another universal generalisation: only celebrities are invited to my party. That's a claim about everyone who's invited to my party. How would we represent it on a diagram? What would go inside the little circle and what would go inside the big circle? Just pause the video for a moment and think about your answer to that question before you go on. Here's the answer: only celebrities are invited to my party means everyone who is invited to my party is a celebrity. So we would represent that like this. The small circle lists all the people invited to my party, and they're all celebrities. They're all contained inside the category of celebrities. But notice this claim, only celebrities are invited to my party, doesn't mean that every celebrity is invited to my party. There could be lots of celebrities who I don't know, who I haven't invited to my party. What about this kind of generalisation? Killing a human being is never justified. Well, we could represent that like this. In the larger box, the domain, we have all the actions that people could perform. And here are the justified ones. And here are the ones that represent killing a human being. And you can see that they don't overlap at all, indicating the idea that nothing in here, none of the killings of human beings are justified actions. Another way you might see this done is by making the circles overlap. So let's just make this killing a human being one a bit bigger, and then people shade out the bit in the middle to indicate there's nothing in there. And that's another way of representing the same idea, that no killing of a human being is ever justified. Here's another way to represent the same generalisation. This should say killing is never justified. Of course, sorry about that. Killing is never justified. Killing a human being is never justified also means this: any killing of a human being is something that's unjustified or not justified. So we can also represent the same generalisation like that. Anything that's a killing of a human being is not justified. So more generally, you can represent a generalisation like this: no A's or B's. With a diagram like this, you have a small circle with the A's, and that's completely contained in the things that are not B. So every A is not a B. That means the same thing as no A is B. No killing of a human being is morally justified means the same thing as this: any killing of a human being is not justified. So we already discussed this in talking about deductive validity, but just to remind you, this kind of diagram representing the claim, the universal generalisation that all A's are B's, can help you remember what does and doesn't follow validly from a universal generalisation. You can see from the diagram, obviously, that anything that's in the A circle is also in the B circle, but it's not true that anything in the B circle is also in the A circle. So all A's are B's doesn't mean that every B is an A. And that's why this kind of argument is invalid. Premise is the generalisation that all A's are B's, or if something's A then it's B. Now we're told that something's B, and we deduce that therefore it's A. Well, that's not valid. It doesn't follow, because the B could be one of the things here, a B that's not A. On the other hand, something else you can see from the diagram is that if something's not in the B circle, if it's out here, then it's automatically not in the A circle. So if something's not in B, it's not in A. So that's why modus tollens is valid. If all A are B, and something's not B, it's out here, then it can't be A either. And why is modus ponens valid? All A are B, or if something's A then it's B. X is A, so X is in here somewhere, well then it's automatically in B, and that's why modus ponens is valid. And what about this one? Denying the antecedent. Well, again, you can read that off the diagram. The premise says all A are B, which is represented on our diagram. The second premise says that X is not A, and the conclusion is that so X is not B. Well, again, here's something that's not A, but it is B, so this doesn't follow. Of course, there could be things that are not A that are also not B, they'd be out here, but just because something is not A doesn't necessarily mean it's not B. So that's why denying the antecedent is invalid. So of these 4 patterns of argument, you can tell which ones are valid and which ones are invalid just by remembering this simple diagram. So we've been talking about what a universal generalization means and how to represent them on a certain kind of diagram. We're going to talk now about how to decide whether they're true or false, and the key idea here is the idea of a counterexample. A counterexample to a universal generalization is a case which shows that the generalization is false. So if we have the generalization all A are B, a counterexample would be an A which wasn't B. That would show that not all A are B, and that therefore the generalization is false. So universal generalization is false if it has some counterexamples. True generalization has no counterexamples. So, for example, here's a famous generalization accepted by most Europeans up until a particular point in history. All swans are white. What would a counterexample be? A swan that wasn't white. Eventually, people found in Australia and elsewhere whole species of swans that weren't white. Those are counterexamples to the generalization. How about this generalization? Killing a human being is never justified. What would a counterexample be? Well, it would be a case of killing a human being which was justified, morally justified we're talking about here. What might some examples of that be? I'll just leave you to pause the video for a minute and think about your answer to that question. What might be some possible cases where killing was justified, or at least could be argued to be justified? Well, here are some possibilities that you might have thought of. Killing a human being in self-defense might sometimes be justified. Perhaps killing someone to save lots of other people might be justified. Killing another soldier in war. We don't usually think that soldiers who, in the normal course of a war, kill other soldiers have done anything morally wrong. And of course some people want to argue that capital punishment, executing people for certain crimes, is sometimes justified. Of course all these cases are controversial, some more controversial than others. Those are just examples of possible kinds of counterexample to a generalization like this. Killing a human being is never justified. There's more detail in the study guide about evaluating universal generalizations like this, and how in the face of counterexamples like this you might want to go back and reformulate the generalization. So perhaps after thinking about counterexamples like these, you would want to reformulate this generalization to say something perhaps like killing an innocent human being is never justified, or killing a human being where other lives are not at stake is never justified, something like that. Notice that those are still universal generalizations, but they've become narrower in scope. But they still say killings of human beings of a certain kind are still never justified, always wrong. Okay, we'll talk now about statistical generalizations. So by a statistical generalisation, I just mean something very simple. A claim that instead of saying all things of a certain kind have a certain feature, a statistical generalisation says that a certain percentage or proportion of things of a certain kind have a particular feature. So, for example, 90% of nurses in Australia are women. 15% of people with ankylosing spondylitis have the HLA marker gene. 12.7% of Australians aged 15 to 24 are unemployed, and so on. So they all say, instead of all A's are B's, they say some percentage of A's are B's. And of course, universal generalisations are, if you like, just the special case where the proportion is 100% or all. So all swans are white can also be thought of as a statistical generalisation that says 100% of swans are white. Sometimes you'll find statistical generalisations where the exact percentage isn't mentioned, but a term like most is used instead, as in these examples. And the majority of Australians do not believe that climate change is a serious issue. Most university places are taken by people who went to a private school. A very important type of statistical generalisation is illustrated by the last four examples here. Male tennis players can serve the ball faster than female tennis players. People who smoke are more likely to develop lung cancer than people who don't smoke. Children who have a lot of sugar in their diet are more likely to be hyperactive than children who don't. This kind of claim compares two groups and tells you that something occurs more often or more frequently, or perhaps less often or less frequently in one group rather than the other. These kind of claims are called correlations or associations, statistical correlations, and we'll talk more about them when we come to talk about causation and arguments for causation. This one, for example, tells us that there's a correlation between developing lung cancer and smoking. As we'll see, that doesn't mean the same thing as saying that smoking causes lung cancer. This is just a purely statistical claim. It compares the rates of lung cancer in two groups, smokers and non-smokers, and tells us that the rate's higher in one group rather than the other. That's evidence that smoking causes lung cancer, but as we'll see, it's not sufficient by itself to establish that there's a causal link. But we'll talk more about that when we talk about arguments for causation. Unlike universal generalizations, a statistical generalization can't be refuted by a single counterexample. For example, if someone claimed that the majority of Australians do not believe that climate change is a serious issue, you can't refute that kind of claim just by pointing out that one or even perhaps lots of Australians do think climate change is a serious issue, because the claim doesn't say all do. It says the majority. So you would need to have evidence about the majority of Australians, not just some, in order to refute that claim. Most university students went to a private school. Well, again, you can't refute that kind of claim by saying none of my university friends went to private school. Well, maybe, but that doesn't refute this kind of generalisation. Many statistical generalisations, the evidence we have for them comes from samples and surveys. So, for example, opinion polls is an example. A recently conducted opinion poll asked 250 adult Australians what they thought were the most serious issues of the day. Only 10% of the sample put climate change at the top of their list. Therefore, we can conclude that the majority of Australians do not believe that climate change is a serious issue. So we have a sample of 250 Australians, and the majority of them apparently didn't think that climate change was an important issue, and conclusion that's drawn is the statistical generalisation that we saw before. The majority of Australians do not believe that climate change is a serious issue. Now, you might think you couldn't possibly get a conclusion about the majority of Australians just from a small sample of 250, but we'll see when we come to talk about inferences like this that that's not necessarily the case. depends how the sample was selected, whether it's representative of the population as a whole. Even quite small samples, depending on the way they're selected, can be representative. We'll talk a lot more about this kind of inference, an inference from a sample to a population, in a later topic. So if you can't use the technique of counterexamples to evaluate statistical generalizations, then how can you think critically about them? Well, here are a number of different kind of questions that you can ask about statistical generalizations. You can ask whether the claim needs some clarification. Is it vague or ambiguous in some way? Can it be made more specific? You can ask questions about how the statistic was derived, what the evidence or argument for it was. If it came from a sample, you can ask questions about the representativeness of that sample, as we'll see when we come to talk about those arguments. Good question to ask is what might explain the statistic. What is the significance of the statistic? What does it imply if it was true? Is it surprising or important, or perhaps just what you might expect? Are there any other relevant statistics that could put it in context? What further implications would it have if it was true? So to see how those questions apply in practice, we'll now look at an example. So here's our example, statistical generalisation reported in The Age, quite some time ago now, so this might not be true anymore, even if it was true then. But never mind, it still makes a good example. Most university students in Victoria went to private schools. So let's go through some of those questions and apply them to this example. The first question you'll remember was, can the claim be clarified? Can it be made more precise? And the answer to that question in this case is yes. If we read the article in more detail, we find that in fact 54% of all the university students in Victoria went to private schools. So that is most, it's over 50%, but it's not a very high proportion. Although for different universities we can see that the exact proportion varies a bit. For the University of Melbourne, 66% of those students went to private schools. For Monash, the figure's 58%. The second question was this: well, how do they know? How was the statistic derived? Where did they get that number, 54%, from? Well, reading the article, we find that it's from a report called Place to Place, based on unpublished Education Department data and written by Monash University researchers, which is all a bit vague. We would have to track down this report and see exactly what methods they use to come up with this figure of 54%. Almost certainly they didn't track every single university student in Victoria. Almost certainly this statistic is based on a sample, so the main question we would want to ask about that is whether their sample is representative of the university students in Victoria as a whole. Let's suppose this is true, though, that 54% of university students in Victoria went to private schools. What might explain that? Why would it be the case that most university students went to private schools? Just pause the video for a moment and think about some possible explanations of this statistic. Well, here are some possible explanations that might have occurred to you. Private school students get better grades. Notice that is itself a statistical generalisation. It's a correlation. It would say that there's a correlation between going to private school and higher grades. That may or may not be true. If it was true, it might explain this statistic that we're interested in. Here's another possible explanation. Universities, especially the more prestigious ones, might have a bias towards admitting private school students. Here's another possible explanation. Well, perhaps about 54% of all students in Victoria attend private schools. If that was true, if most Year 12 students go to private schools, then that would explain why most university students to private schools. And of course, there are lots of other possible explanations. These are interesting to think about because they're relevant to what further conclusions you might draw from this statistical generalisation. Which brings us to this question: what is the significance of the statistic? This number, 54%, wouldn't be all that surprising if about 54% of all students in Victoria went to private schools. Then you would expect 54% of university students to have gone to private schools. The article tells us that in fact that's not true. It says that in fact only about 40% of all Year 12 students go to private schools, 60% go to public schools, so about 40% go to private schools. So it does look like we have an over-representation, if you like, of private school students at universities in Victoria, but not a huge over-representation. It's the difference between 40% and 54%. So that puts the statistic in some kind of context and tells you something about its significance, about its meaning. Are there any other relevant statistics? Well, the article itself mentions quite a few. For example, this interesting one, that only 31% of government school Year 12 students went on to university in the year before this article was published. I just want to use this number to draw your attention to something. This statistic tells us that 54% of all university students in Victoria went to private schools. And from that we can deduce that 46%, the remainder of those university students in Victoria, went to public schools. So 46% of university students in Victoria went to public schools, government schools. That does not mean the same thing as 46% of students at government schools go to university. In fact, this statistic tells us that the number is much lower. Only 31% of government school students go on to university. That's compared to 66% of independent school and 48% of Catholic school students going on to university. So much higher rates of students go on to university from private schools than from government schools. We also have this statistic here which tells us about the difference between enter scores, grades, going into university between government school students and private school students. It tells us this is a correlation. This claim, it compares two groups and tells us that an enter score of 90 or more occurs much more often in private school group than in the state school group. Finally, we can think about this question. If assuming this statistical claim is true, what implications should it have? People don't usually just give statistics for no reason at all. They want to present them as part of an argument, as a premise in an argument. So they think that the statistic has some implication, some further implication. Typically a claim about something we should do. We should do something about this. Public school students are underrepresented at universities. Something should be done. Here's what the authors of the report that this newspaper article was based on said. They argued that the findings eroded the claims of successive federal governments to a commitment to improve access to university for people from low and middle socio-economic backgrounds. The proportion of university students from low economic backgrounds has hardly changed since the late 1980s. Notice that's a different claim, this statistic at the end, to the one that we had before. This doesn't say anything about people from low and middle socio-economic backgrounds. It says something about the proportion of university students who went to private versus public schools. So that raises the question, well, what proportion of public versus private school students are from low to middle socio-economic backgrounds? Just returning to the original claim about 54% of university students in Victoria going to private schools, that is a slight over-representation of private school students. Another kind of question you might ask is it increasing or decreasing? If it's decreasing, and has been decreasing for a while, you might say, well, the trend is downward, and so perhaps we don't really need to do anything more. If the trend was upwards, on the other hand, and you thought it was important that private school students weren't overrepresented in universities, then you might think it would follow that we should try and do something about it to change this statistic. And of course there are many other questions you could ask about this. Just to summarise, there are two basic kinds of question you can ask about a statistical generalisation like this. How do they know? Where does it come from? And if the statistic is based on a sample or survey, you might be able to evaluate the reliability of that survey. As I said, we'll talk about that more in a later topic. The other kind of question is about, well, what follows? Assuming that statistic is true, what can we infer from it? What conclusions can we draw? And that can depend on answers to lots of these other questions, like what would explain the statistic? What are other relevant statistics? What's the context? Is the trend up or down? But we'll leave this example here.